But yeah, so while the slides get pulled up, I'm Hunter Westcott. Going to show you some stuff from modeling. So keep in mind all that beautiful stuff from what people do in the real world. We're going to take a step into the virtual world for a little bit to understand how some of these things go. So ISRU of water. Why do we care about this? Water is very vital to our survival. As many of you may know, we need to drink a lot of water to survive, but it's also very expensive to send things into space. I think a few of us a couple days ago were talking about, just sending a cover for an instrument was going to cost an extra $50 million for a single piece of fabric. Imagine how much that would go up to with water, because that's quite heavy. But we know there's ice in some regards, and especially in these permanently shattered regions. Currently, I think about 5% of ice is in there. But we also know from other simulation work that it's stable for very long periods of time, which is quite good because we want to be able to get as much of it as possible. And the moon's been around for a long time. So the longer it's been around, theoretically, the more that we should be able to get. But here's what probably many of you have seen before, the candidate Artemis landing regions. And I don't necessarily point this out to say this is where we're going to land, but to get a general scale of what we're looking at here, where there's a lot of large craters in there. And that's typically what a lot of people want to go after first, something that's a little bit bigger, a little bit easier to grab. But there's a case for small craters. They're a little bit easier to get to. They're abundant. This is just, a small sampling of some things that we get, but there's no reason that these smaller craters can't hold a significant amount of water ice. Some are permanently shadowed, some are not. So it's the idea of, how these small craters can hold water ice in them. So we come through a lot of the LOLA data, that's what's here, and decided to put that into a simulation. So we extended our thermal water extraction on the moon into no longer doing necessarily extraction, but just general volatile motion through thermal motions. Originally, it was written Fortran, and we've extended it to do some GPU acceleration to make things go a little bit quicker. And then, we got the LOLA data and imported as a 3D voxel. And then we also did a simple solar flux modeling just to, get over a longer time scale how not just necessarily the heat of impact is going to affect these things, but just generally how existing on the lunar surface is going to impact them. So this is a lovely crater that we found somewhere in that region on the South Pole. But, it's about 15 meters in radius. I think it's about 25 meters in height. Elevation total is about 25 meters in depth. So it's very, very small when we're talking about craters. Typically we're talking about these kilometer-sized structures. We subdivided these into 80 by 80 by 15 individual cells. So that brings us about to 2.5 meter resolution in every direction. Something that may not be terribly realistic here, but just for an initial kind of upper or lower bound on what we're expecting on how this model to perform, we assumed that an impact was going to deposit about 0.5 kilogram of water over the surface. So each cell has about 0.5 kilogram of water, just so we can truly get an idea of how this motion is going to work in a very, very extreme case scenario. And then from there, we started at the beginning of the lunar day. So that way, as time goes on, the sun will rise and set and keep going. So this is what it looked like at the end of the day, temperature-wise. Pretty cool. It's about what we expect in the lunar South Polar region, especially having sun exposure. So it's good to see that. But we also see the insulatory capabilities of the regolith, where the heat is taking a little bit longer to dissipate, as we start getting deeper into 5-10 meter depth of the lunar surface. Now, for the more interesting things here is how all of the ice and the vapor go over time. It's a little bit hard to see, but at the initial part, we have a lot of vapor, and then it all just kind of sinks into the lunar regolith and starts to freeze. And as the day and night cycles continue, we start to see that there's a change in how much is sublimating and refreezing during the day, which we plotted here where we can see kind of how it goes. And while there's certainly definitely a limit to how much ice is going to be there, in this case, we see that there's definitely a plateau where not all of the vapor necessarily refreezes. There's definitely some being lost into the lunar exosphere. And we plan to look at that a little bit more, exactly how much we're losing, at what rate we're losing. But it's very important to notice that, the ice is freezing within the first 5 meters, even from an extreme example like this. So we can expect to see, within the first 5, maybe 10 meters, there to be a significant presence of actual ice, not necessarily surface frost as what we think might be some low-hanging fruit. Just kind of wrap it up. I know it's a little bit of a shorter one, but yeah, we expect to see within the first 5 meters, but it's important to know that these can also probably occur in things that aren't permanently shadowed regions. Permanently shadowed regions definitely help the case for having ice, but the insulatory property of regolith, as we've seen from some other presentations today in the dust section, that it's quite well at insulating, and even if the top couple tens of meters get a lot of solar flux, it's still realistic to probably have some amount of ice that we can access down there in the craters. So thank you.
We have some time for questions.
So does the ice kind of just uniformly sink down? Does it accumulate? Like, does the topography make much of a difference?
The topography we're noticing does actually have some difference in there, where it's not just all uniformly going down. We see that along kind of, what we define as the slope ridges. It actually settles a little bit quicker than the parts that are a little bit more surrounded by, more soil and, some slopes, some just, ingrained, compressed rock there, which is also an important thing, that it definitely follows the surface topology. And it's going to be interesting to see how in more complex craters, this one was very circular, but there's plenty, especially from secondary impacting, how that's going to impact things, because if it's following, the topology, we have the secondary impact at a different, angle. How is that going to redistribute all those volatiles?
Yeah, even have more time, like. But if not, well, thanks again. And oh, no, there was a question. Okay, sorry.
No,
I have to walk
good.
back, but go for it.
Yeah, what do you think the effects are? Like, how do you think things change on different crater size scales? Because you said you're just doing kind of the smaller ones, but I was wondering, like, if you get really tiny or a little bigger, like, what are the effects?
So the effects are mainly going to be due to the actual size of the impactor. Here it was very unrealistic. It was basically a solid piece of ice making this small crater. But the larger the impactor is, the more material that's going to be brought with it. So you'd expect the more volume you have. If you do ice by volume percentage, more volume, more water that's going to come there with it. So you'd expect to have more water. But it's also too that the size of the crater is related to the actual size of the impactor. So a lot of your material is probably going to be a lot more confined to the actual center impact rather than more of the edges as the ejector blanket gets folded out. So you'd probably see a more concentration as you move towards the center of the crater.